Hello and welcome back to Calculus 2, section 7.2 on exponential models. Guys, these are word problems. 100% of them word problems. And it's going to be all walks of life now. We'll see. These problems you learned in a basic form all the way back in your pre-calculus course when you learned word problems for exponential problems. You learned that there is this formula, y equals a e to the, let's say, kx, as a basic formula, and the graph that went along with it looked like that. The y, a was the y-intercept, you have x, and it was called exponential model. And you did a whole bunch of problems, word problems, that were including the population growth, money growth, and then decay problems, so the garbage decay, radioactive decay. You also did carbon dating to check how old something organic that you dug up is, and so on. So a lot of problems you solved. We are going to repeat all of those problems tonight, the same, 100%, and then we are going to add an extra component on top of them. So, since we know derivatives, limits, derivatives, and integrals, we can predict the future with them. We can see the change, instantaneous change, and we can calculate the accumulation of different situations. We'll see, for instance, how many people lived between this year and that year, and you can calculate stuff like that with integrals. So we are going to do the same thing we did in pre-calc, and then we're just going to add the calculus analysis using these three on top of it. I like to start with the population, so we can show that the basic population model we learned in school is terrible. Population P of t. So population P in time t, clearly you have to wait for population to change, whether the population is growing or population is decreasing, decaying, right? The change in population will be detected through later on derivative and so on. But now we are going to recast our formula from up there into our, that was a nice one, population is initial population e to the k t. T is going to be in terms of the years, so t is time in years. And you will have to be careful when you are dealing with population, because population could be given in a problem, population in millions, population in thousands, or just population. That means units, right? Single unit. Unit 1, Unit 2, Unit 3, Unit 4, right? So, but they also can represent thousands. So 1, 2, 3, 4, 4,000. So you have to be careful what is given in the text. Now, does time have to be in years? No. Bacteria tends to work in less than a year, right? So you can have minutes, you can have hours for bacteria growth, and so on. So not everything is in years, and not every population is the unit. In general, you know, we say P0 initial population, and that happens when time is equal to 0. That's very important. That's why it's called initial, right? That's the beginning of your problem. And everything starts from there. You don't care what happened prior to that point. So now we can use this model to go on and go to the website called Population Clock. It is a .gov. It's a census.gov website, which is the government website, which shows the population, the way the population ticks. Now you have the US on the left, you have the world population on the right, we see that we are at 7.6 billion on the planet, and we would like to just, take a look and come up with some kind of exponential model that will show which way this population changes. Now you have the US over there sitting at 330 million people, and if you scroll down, you will see the 10 most populous countries in the world. China, followed by India, followed by United States, followed by Indonesia. Last year is that Mexico overtook Japan because Japan is slowly dying out with the negative population for years now. And
So
Japan and Germany too. So, and US now for the last 2 years, I believe, with a negative influx of babies. The population growth over there is due to immigration, not due to population here, because you can find the data on decaying U.S. population. Japan has the largest one, so they actually lost their 10th spot to Mexico last year. So now I'm not sure if Japan is probably now 11th, probably, I don't know. So now what am I going to do for this particular problem? Well, I want to just, play with the population of the world. In this case, I'm going to call that 7.6 billion people. So population now is 7.6 billion. Now what I want to know is, let's pick a year and then figure out what the population was sometimes in the past, because we can ask Google, and then then work out the model and come up with the mathematical model, the lame one, but still, it's a model. So, world population in 2002. Yeah, 6.281 billion. How about we do 1970? 1437. 1970. Oh, wow. Is that 50 years ago? 50 years. That's a generation of your parents. Yeah. Okay. They were in school or, elementary or middle school or something. Or crying. Half. Less than half, right? So let's use this. 1970. Population is 3.7 billion. That's all I need. I just need I need a point in time somewhere, and we're good to go. So let's take a look. I have population now is 7.6 billion. In 1970, population is 3.7 billion. That's all I need. So this is what I'm going to do. I'm going to set this as initial value, which means that I am going to say that t is equal to 0 in 1970. Okay? 1970 is t equals to 0. So now, from this, I can calculate, well, I have my first point, 0, 3.7. And because it's initial point, my P of t model is 3.7 e to the kt. Because 3.7 is initial population. Initial population happens when t is equal to 0, and we just picked this year to be 0 year. You can pick any year to be 0 year, right? Let's go with 1970. Now, situation now is 2019. That's 49 years later, right? So this point is 49, comma, 7.6. That's today. So 49 years later, 49 years later to get to 2019, where the population is 7.6 billion. So now we use that information and this information to write that 7.6 billion grew from 3.7 billion E to the unknown constant K times 49 years of population growth. So I plug in this is my T comma P points, right? T for time and P for population. So if I have now my exponential model was P equal P0 e to the kt, so I know that P0 is when the T0, and we just have this. Now see, we have the exponential equation which can calculate K. This K is what gets the population to go up or what gets population to go down, right? Depending on whether K is positive or negative. Positive K, population grows. Negative K, population decays, gets smaller. And this is a very bad model, but it's, it's at least some kind of model. You are going to learn better population models when you take differential equations. You will spend about 5 minutes on this, and then you will go to much better things. So we start here by calculating this. We're going to divide 7.6 by 3.7 first. So 7.6 divided by 3.7 is going to give us 2.054, and that's going to be equal to e to the 49k. We're going to hit both sides by ln to kill the e, and this is that's the conversion thing that we talked about last class. So ln of 2.054, and please remember to use 4 significant digits. It's not 4 decimal places, it's a 4 non-zero decimal places. So in this case I have 0.7198 when I round, and on the other side I have 49k. Now I divide both sides by 49 to get k alone, and I get that the k is equal to the 0.0. And see, those do not count because those are all zeros. 4 decimals start now. 1469. 1468, and then this one rounds up to 9. Good. So with this, I have the population model for the world population starting at 1970. So it's P of t equals to 3.7 e to the 0.01469 t. And this would be exponential model of world population, right? Why do I say this is terrible? It's terrible because if you take the limit of this model as t goes to infinity, you will get that the population will be infinite, right? So if I just check this real quick and I say limit as t goes to infinity, this is what you're going to do in differential equations, going to be 3.7 e to the 0.01469 t is going to give you infinity. Now, what do we know about our planet? Well, first of all, It's round. Stupid. The next one is, it's a finite surface area, right? If it's a finite surface area, you cannot fit infinite people, infinite ants, infinite anything on a surface of a finite planet size. So, this model is clearly terrible because it doesn't predict when we reach what is called carrying capacity of the planet. Scientists can agree whether it's 10 billion or 15 billion or 12.1 billion, whatever it is, depending on which averages you're using or so on, right? But we can calculate using we can pick any number we want between 10 and 15. Pick something. I said 10 to 15, you said 5. 15. So how long will it, now, I want to know how long to reach, by how long in terms of time, how long will it take for population to grow to 15 billion? Well, you know that your target is p equals 15. You have the exponential model, plug it in. This is not calculus, right? So 15 equals 3.7 e to the 0.01469 t. Divide and use ln. So 15 divided by 3.7 is 4.054 equals to e, leave some space for ln, 0.1469 t. Hit both sides by ln. That will kill off e. So you have ln of the answer over there, which gives you 1.3997 is equal to 0.01469 t, because ln and e canceled. And you have this number divided by 0.01469, which gives us 95.28. You call that 95 years. Is that 95 years from today? From 1970. Very good. Our problem started in 1970 because we set that to be our zero. So it is going to be 1970 plus 95, right, to reach 15 billion using this model. So that is 2065. Nice, right? To reach 15 billion people looking at this model. Such is life, right? Now, obviously, if the carrying capacity of the planet is 11 billion, then issues, right? So, you are guys going to learn in differential equations better models. Logistics model is the better model because that model takes in consideration carrying capacity of the planet. You see, the reason why this model is terrible is because when you look at its limit, right, it's just the exponential function that goes like that. So over here you have your 3.7 billion on population, and then you have your time, and the graph just, goes up its exponential function. Logistics model actually caps off at the carrying capacity. Because when you reach carrying capacity on the planet, that means there are no more resources. You can't produce more food than what planet can sustain, because there's no more area to produce food, right? There is no more livable air. We don't live very well underwater and in deserts and on, polar caps. I mean, do we have some people living there? Sure. it's an insignificant portion of the population that it's able to adapt to those conditions. How about you go try? For like 15 minutes, you'll be crying back here, right? So, the logistics problem would have a graph something like this. It starts at initial, and then it flattens. And then the flattening can be war, can be hunger, can be anything, because any extra you're adding to the carrying capacity is not going to make it. It's very, very simple. So those kind of models, including also predator-prey models for population and so on, right? It's not, because can you really use this model to calculate the population of rabbits? No, because rabbit is pretty much eaten by everything, right? So they multiply, but they get eaten as well. And it's balanced, right? Otherwise we'll be drowning in rabbits, or it will be extinct. So the nature has this perfect balance. Interestingly, you take cats outside of the equation, we all die within 2 years as a species. Human species dies within 2 years if you take cats off the planet. Look it up. You know what you take? You know what species you take out to die faster than that? Bees. Bees pollinate 75% of our food. Someone says, well, I eat meat. Yeah, but what the cow ate, right? If you eat a cow, what did the cow eat? So, yeah, bees and cats. Take any of those two, we don't have much time left on the planet. Look it up. So, population games, right, are very tricky. So now what can I do with this? I have an exponential model. I can calculate, using the derivative, I can calculate how many people you get to add in any year of your choice. So, let's calculate how many new people we are going to add this year to the planet, right? Earth. So 2019. So the first order of business is to find the derivative of the population, and then you will run that formula at 49, because this is the year 49 away from 70. So if you have your population problem, P of t, to be 3.7 e to the 0.01469 t, you find the derivative p prime of t. Well, that's going to be, right, your exponential model. We did that. That's the a. Remember the e to the ax? The a, which is the decimal, drops in front and multiplies into 3.7. So 3.7 times, that was a good one, 0.01469 is going to be 0.05435 e to the 0.01469 t. So that's our derivative. And now if I want to know how many people we added, right, I'll put 2019 here. 2019 is t equals 49. We established that. I just need to plug in 49 into t and punch numbers in the calculator. So 0.05435 e to the 0.01469 times 49. It will give you in billions how many people we add just in 1 year. So times e caret, open parenthesis, 0.01469 times 49, and that gives me 0.1116, so 112 billion. How much is that? 112 million. We are going to add this year 1/3 of US population to the world. I mean, not us, I mean, the world is going to grow by 110 million, let's say, in 1 year. It is. But it's exponential growth, right? If you want to know how many people were around, let's say, in 90s, how many people do we have in 90s? You are going to do the definite integral of the model for 90s, and that's from 20 to 30, right? Because if you do 70 plus 20 is 90, and then, sorry, not 20 to 30, 20 to 29, right? 20 to 29, and you have the 10 years of 90s, and whatever that integral spits out is going to be the amount of people alive living on the planet in between in those 10 years, 90s. So you can calculate a lot of these things and do a lot of analysis if you know calculus in terms of limits, right? To approximate how many people you're going to have in whatever amount of years, because you just say, how many people I'm going to have in a year, blah, blah, blah. Well, the limit goes to that year. Derivative will calculate the amount of people you add in a particular year. You just need to make sure that you are plugging in the correct number. Since we did in 2019, we used 49 because they're 49 years away from 1970. And then integral can be used to calculate the accumulation of people because that sums. So these are your growth problems. You can talk about growth of money in the account with compounding. You can do population problems. There are a whole bunch of different things that you can do with this. The other side of the coin is going to be decay problems, where the amounts are diminishing and your K constant is negative. So that's how you know that you are losing whatever you have, whether it's a mass or population or money, right? So if you're talking about decay, you are looking at the model y equals a e to the negative kt, and the graph turns around, and in time, graph is trying to reach a zero. It will never reach a zero, but it's trying to. So, a couple of good problems that you can work over here. Carbon dating is one. Let's say you dig up a scroll of some sort. Well, the scroll long time ago was made out of plants, made out of trees, right? That's organic compound. It's going to have a carbon C14 in it, and you are going to have a half-life and so on. So let's talk about half-life first. So, Half-Life is one of the best video games that Half-Life lambda is the time in which the mass decays to half of its original value. Actually, not original, initial value, of its initial value. So when we say half-life, half-life is time. And for different things, as different amount of years or days or minutes or seconds. Some particles decay in a fraction of a second. Some particles decay a long time. Some radioactive materials take thousands of years to decay. You can use these particles to make atomic clocks, which are the most precise clocks we have on the planet. And then you sync your clock with it, and then you're still late. Right? So there's a lot of things you can do with this. Now, these decay problems are very important to us, not just for carbon dating so we can study history, but we want to manage garbage decay, right? Because there's a lot of garbage that we generate. Imagine how many households, in United States. It's like over 120 million households in United States, and everyone is going to have at least a bag of garbage every week. Some households, 2 bags of garbage every week, right? That's 120 million garbage bags a week. Where is that going? We're not shooting into space, right? And that's just this. So garbage management, garbage decay from our ecological, right, standpoint is very important. Most of the time, right, what do? We bury it in the ground and we put some soil on it, put some grass on it, and a few years later, build a development on it, and then the kids have 3 heads and 15 legs, right? But that's exactly what's happening, right? We need to manage all of those things. Then we have the radioactive decay, right? Not just the fuel that we use for fission now, because we don't have anything better, but there's a whole bunch of stuff that, you know, that we have to worry about. And, you know, these problems have a merit. So I'm going to talk about my favorite problem of all time, so we can see some of this stuff in action. And that is doormat. He's going to look it up right now, right? I'm going to show it. Doormat is awesome. Doormat is the first ever tooth whitening toothpaste.
Oh, no. Definitely got some bad stuff. Say radioactive.
Yeah, doormat. You never heard of doormat? Well, now you did. 1943, they came up with the amazing tooth whitening toothpaste, first one on the market ever. And they used thorium-229 because apparently when you use the isotope of thorium on the teeth, it gives it a beautiful white glow. Small issue with it, everyone who brushed died quickly.
Oh my God.
Within few years, because it's 1940s, what do you know, right? So as it started, as you can see, it starts with a nice advertisement and commercials, just like Xanax and other stuff, and then it goes down to stuff like let's see, eventually. Come on.
There you go.
I don't know. Well, they changed. Oh, there they are. Haha. Right? Then you end up with it, right? Eventually. So when science is not there and then something is pushed, right? You didn't research it, you didn't learn a lot about it, right? And then you end up being guinea pig for it. Well, and you know, stuff like this. So we are never smartest, you know, at the moment. Watch someone like 300, well, you can't. Watch someone like 300 years say, they used to drink milk. That's why. That's why they only live. That's why they only live 100 years, right?
We live 1,000 years.
Yeah, we never tried a drop of milk, and we live like 1,000 years off the bat, right? That's just like a first thing. Like we don't know, right? It's just science pushes something. So now, guys, what's happening with this doormat thing, right? The entire toothpaste is laced with thorium-229, and the thorium-229 is a highly potent radioactive element. It's going to give a beautiful glow to the teeth. The issue is that the half-life of doormat is, as you can see, because I did pull the chart, thorium-229 half-life over here listed as 7,340 years on half-life. So here we go. We're going to write doormat, thorium, 229, half-life lambda, 7,340 years in the decay. And now I'm going to switch because you have seen the tubes, you have seen the commercial and all that kind of stuff for it, the advertising. And now we can just work out this problem. So now, what am I interested in? Well, the people that brushed when this thing came out are dead 70 years already, right? 70 years? 80 years? But let's call it 70 years, doesn't matter, right? So I want to know what amount, percent-wise, what amount of thorium is still on their teeth. They're dead 70 years already, right? I just want to know what amount of thorium is left on their teeth, the deposits, 70 years later. And for that, we are going to calculate using this. So first off, we have that our mass is equal to initial mass e to the k t. It's the same model as we had. You used P's before, right, for population. Now use M for mass. Now for half-life, the red definition up there tells us that if we use the half-life in the equation for T, we are going to take initial mass and cut it in half. So at half-life, I have mass is cut in half, e to the k lambda. Because my time at half-life, t equals lambda, right? Now you see that these initial mass drops. Maybe, some people over time put, 1 milligram, some people put 1.5 milligrams, whatever. So this problem turns out into 1/2 is equal to e to the 7,340 k, because that's what lambda is, our half-life for the problem. Now we're going to hit both sides by ln to calculate k for our problem. And we have to calculate ln of 1/2, so ln of 0.5, which is going to be negative 0.6931. And on the other side, we have 7,340 k. When you divide by 7,340, you get k equals 0.0000, 4 zeros, and then 9443. Remember, 4 significant digits, so we don't have a lot of rounding error in our calculations. So my thorium-229 exponential model for decay, it's negative. Oops, guys, negative, decay. So my thorium, his mass is equal to initial mass e to the negative 0.00009443 t. This is the model that we are interested in. And now I would like to see, after 70 years, what is the amount of thorium that is still on the teeth? So, what percent of thorium-229 is still on the teeth after 70 years? Wait, we are closer to 80 years, right?
Sure. Is it just 1940 or like 1949?
Well, if we go from 70 years, because if you say it came out at 43, so let's go from 50 to 20, right? So that's 70 years. Fine. All right. So what are we going to do? Well, I'm going to say that, see, it says what percent of the initial mass, right? So what percent, in like a percent P, of initial mass m is there after all this time, 9443 times 70 years up there. So initial mass drops again, right? Again, everyone brushed more, less, right? So initial mass really doesn't matter, as you can see. And we can calculate the percent p, because you know that you calculate percent when you multiply percent into a value, so p times m. I have to calculate this expression e raised to this thing. So e raised to the open parenthesis, answer from before, times 70, and I get 0.993.
Oh, I didn't make it.
So what's the percent? 99.3% left. These are this is the most beautiful corpses ever, right? They all have the white glow, yes, the bright smile, right? Anyway, so yeah, radioactive elements, not a joke, right? Not a joke. Which is why we need fusion as soon as possible, guys. You put hydrogen on one end, you have helium and water on the other, and all the energy you want in between. Woohoo! Which is the problem, it's always 30 years away. Anyway, so when we have the mathematical model, can I do the limit? Yeah. If I send time to infinity for exponential model, what am I going to get?
0.
0. So my question to you is, when will the thorium go away? And the answer is? Never. Why never? It's never because this planet has the expiration date. Right? Give it 5 billion years, which is nothing compared to infinity you want to send this to, this planet should be gone, right? So, okay, yeah, it's green, but such is life. And now this brings me to the next problem that I like to work out, and that is, you can use these same calculations and same things to calculate the way the drug metabolizes in the system. You can go online and look up the medication and take a look at its half-life as it metabolizes in the body. When you have a pill of some kind, you take it, it's not effective at its full strength right away. It takes time to work its way out through the system. Advil is rated at 1.9 hours of biological half-life, and we can round that to 2. So what is the recommended dose for Advil? Every 4 hours. Now, people, in their infinite wisdom, go like this. Oh, even if they heard of biological half-life. Half in the first 2 hours, half in the second, well, we are ready. Hell no, you're not ready. But okay, let's see. So let's just work some of these exponential models, and I'm going to use Advil, and then we're going to say, let's say you took a dose of 500 milligrams, which I believe are 2 pills or whatever it is, I don't even know. But anyway, so Advil, lambda equals 2 hours. And let's say this is going to be algebraic calculation. And then we can go and do some math if you want to. So you take 500 milligrams now. What happens 2 hours later? How much is left in your bloodstream? 250, right? Because half-life cuts the original amount in half. What happens in the next 2 hours? goes to 125. Well, isn't that 4 hours later? So what do? You pop another dose of it. So how much do you have? 625 now. Wait 2 hours. You see that with each dose, the concentration in the bloodstream increases. Right? Ton, 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 exactly. Now, what kind of the decay are we talking about? Exponential decay. So if we work out the same problem like this one over here, except instead of 7,000 years, I put 2 hours, and I think you can run through this calculation if you change this number with 2, you will come up with a model for Advil. Now that model is also going to have a negative number because the amount of Advil in the system. Aspirin, Xanax, I don't care what it is. They all have that half-life thing. What kind of graph do they have? What is this kind of graph? The exponential decay graph. This is you taking 500 milligrams right here as the initial dose, and you don't take ever again. How long before it's 0? Oh, brr, right? Yeah, if we had the good machines, they should be able to tell every single thing you ever took forever and ever and ever, right? Because it doesn't go away. It's a simple, right, graph right there. Now, as you go, right, you can use your free license that you have with Mathematica, right? And or you can go to the website like Wolfram Alpha, and you can type in the medication in Mathematica. Then you wait a little bit, and then they give you, the name is ibuprofen. If you want to cook it at home, it's right there, right? They have all of the stuff that you might want to know. Go down, go down, go down, go down, go down, and eventually, boom, there it is. Tells you how it interacts with other drugs and so on, right? It gives you all of the mathematics. And it's not just Advil, it's anything you can possibly have in the market because they compile these databases. And then you can run these calculations on your own, right? You can see, so technically, any medication that you are taking at the end, when they have the decreasing dose, actually needs to be followed because it is supposed to reduce the amounts of, right? Because remember what I did with the Advil over there. 4 hours later, there was 125 left. I added another 500, and boom, 625. But they will say take half of the pill. So now, if it's half of the pill, then it's not another 500. It's 250 plus 125, right? It's 375. That's less than 625. So, if any one of those, right, guys, these things are calculated. It's not like, oh, let's just run a trial on 50,000 people, see what happens. They used to do that in World War II. No. Now, you get to compute these things. So I don't care if you are a bio major or you are engineering major or whatever major, this is the calculation for that. Someone has to compute these things, and then it has to be observed, right, when it's deemed that it should be safe even for trials. And then it has to be verified and re-verified and verified, which is why all of these drug companies have this as the highest secrets. They never release it until they are ready to actually make money off it. That's why I have viruses for Windows machines, because all of this is run on Windows. And that's why people write viruses for it. Someone says, no, I use Apple, there's no viruses. Well, no one needs anything off of it. So of course no one's going to write anything for it, just nothing on it. but companies that actually run this stuff, right? There's something to steal, right? So you're gonna write viruses by billions. So I hope you guys got the glimpse of these calculations, and the best course of action, if all of this today looked foreign to you, is to actually take care of the pre-calculus portion first by looking at exponential word problems in the pre-calculus book. And then, on top of that, you get to add limits, derivatives, and integration, because you need to be able to come up with a model to calculate that k first. And when you calculate that k, you have exponential model which you can manipulate through whatever calculus procedure, right? You need to go on. I'm going to open the homework now, guys. One more section left, and we are done with